In the last lecture, we talked about measures of center. We talked about the mean, the median, and the mode. Here, I have wait times at two restaurants. If you calculate the mean and median for these two restaurants, you'll find that they have exactly the same mean and exactly the same median. So just knowing about the center of the data doesn't tell us the full story, because at one of these restaurants, the wait times are way more spread out than the other. Today, we'll talk about numbers that tell us something about how spread out our data is. The main measure of spread we're going to talk about is the standard deviation. What is the standard deviation? So the idea behind the standard deviation is we want to find the average distance of the data from the center. Now, another word for distance is deviation, and that's where the name comes from. Deviation just means distance. So we're looking for the average distance or deviation of the data from the center. And in the last lecture, we talked about three measures of center. We talked about the mean, the median, and the mode. The center we're going to use is the mean. So the standard deviation is the average distance of the data from the mean. So let me try to work my way through this idea and see if we can calculate the standard deviation. So first thing I'm going to do is I'm going to list out all of my data. So my data here is, these are wait times at Olive Garden. My data is 54, 57, 63, 65, and 66. So I want to find the distances from the center, or distances from the mean, which means I first need to know the mean. So what's the mean? We know how to calculate the mean. All we need to do is add up the data values and then divide by however many data values we have. All right, so we'll first find the mean. We'll add up the data values. So 54 plus 57 plus 63 plus 65 plus 66 divided by however many data values we have. 1, 2, 3, 4, 5. Enter this into my calculator. Up top, 54 plus 57 plus 63 plus 65 plus 66. On the bottom, 5. And I get 61 exactly. Okay, so now I want to find the distances from 61, because 61 is our mean. How far is 54 from 61? It's 7 away, and I'm going to write it as 7, negative 7, to indicate that 54 is 7 below 61. And really the math we're doing here is we're subtracting. So 54 minus 61, you'll get negative 7. How far is 57 from 61? Subtract 57 minus 61. Negative 4. And all that means is that 57 is 4 below 61. 63. 63 minus 61 is positive 2. The positive just means that 63 is 2 above 61. 65. How far is 65 from 61? Subtract 65 minus 61. Positive 4. And then 66. How far is 66 from 61? Subtract 66 minus 61 is positive 5. Okay, so the math we're doing here is we're subtracting, but the interpretation you should be thinking of is these are telling me how far each of these data values are from the mean, the center. Okay, and the plus 5 means that 66 is 5 above 61. Okay, these are my deviations or my distances. And what I would like to do is find the average of these distances. But there's a problem. Okay, what happens when I find the average? So the average meaning I would add these up and then divide by 5. So what happens when I add this up? -7 plus -4 plus 2 plus 4 plus 5. Try it. -7 plus -4 plus 2 plus 4 plus 5. I get 0. And that's actually always the case. That's a special property of the mean. Anytime you look at the deviations or distances from the mean and you add them up, you're always going to get 0. So that's a special property of the mean. So the mean is the center in the sense that it balances the distances above with the distances below. Okay, so that you always get 0. Now, that's a problem because if this is always going to be 0, and I want to find the average of this, I'm always going to get 0. And I don't want to always get 0 as my answer, right? Because then it's not useful to me if the answer is always 0. And the problem is that we have some positives and we have some negatives. And that's what's causing the 0 to happen. So the next idea is, if the negatives are my problem, I need to get rid of the negatives. How do I get rid of the negatives? Well, one way in math to get rid of negatives is to square things. So that's what we'll do. We'll square things. So we'll take these deviations and we'll square them. Okay, and that will get rid of the negatives. So -7 squared, that just means -7 times -7. That's a positive 49. -4 squared, that means -4 times -4. That's a positive 16. 2 squared, 2 times 2, that's a 4. 4 squared, that's 4 times 4, that's a 16. 5 squared, 25. 5 times 5. Okay, I squared things, now everything is positive. Now I don't have that issue of things adding up to 0. And the idea is, I'll take the average of these. Okay, so we'll average these. And that just means we're going to add them up. And then normally when we find an average, we would divide by however many values we have. Now we have 1, 2, 3, 4, 5. Now, this is going to be slightly weird, but instead of dividing by 5, I'm going to divide by 1 less than 5, 4. And I'll explain why later on. Okay, so this is kind of an average, but instead of dividing by 1, 2, 3, 4, 5, we're going to divide by 1 less than that, 5 minus 1, which is 4. Now let's see what this is. Up top, 49 plus 16 plus 4 plus 16 plus 25. On the bottom, 4. 27.5. And that's kind of an average of the deviation squared, this last column. Now, what I really want is the average of the regular deviations, not the deviation squared. So as a last step, I'm going to undo the square. So in math, how do you undo a square? To undo a square, you're going to take a square root. So now we're going to take a square root. On my calculator, I'll do a square root of 27.5. And then round to 3 decimal places. And we get 5.244. And that's the standard deviation. We just saw the overall idea of what a standard deviation is. It's just the average distance of our data from the center, and the center meaning the mean. Let me now introduce the actual formula for standard deviation. So before I do that, I need to talk about some symbols. And there's going to be a population version of the symbols and a sample version of the symbol. Population, remember, means just everybody. Sample means a smaller subcollection of the population. Number of data values. If we're talking about the population, it'll be a capital N. If we're talking about a sample, it's a lowercase n. The mean. If we're talking about a population, the symbol is mu. That's a Greek letter mu. If we're talking about a sample, it's x bar. So in other words, if you were able to calculate the mean or the average from data that you got from everybody, you would use this symbol. If you got the mean from just a sample, you use this symbol, okay? The way you calculate, exactly the same, the symbol is different. Standard deviation, if it's from a population, the symbol is a sigma. If it's from a sample, the symbol is lowercase s. Variance, the symbol is sigma, so this thing, squared. If it's from a sample, the symbol is s squared. The variance is basically you take your standard deviation and you square it. Now, these are the two formulas for standard deviation. There's a population version and then there's a sample version. Now, for this class, we're focusing just on the sample version. But I just want you to know that the other formulas do exist. Now, let's look at these two formulas and look at what's different. That's the symbol for population standard deviation. That's the symbol for sample standard deviation. Now, the x, little x, that's our data. Okay, and that's the same in both. This symbol, which is right here, is the mean. This symbol, which is right here, is also the mean, but it's the sample version of the mean. This n, that's the number of data values. This n is the number of data values. Now, both formulas are really telling you to do almost exactly the same thing. Data minus the mean. Data minus the mean. The only thing that's different is on the bottom. For the population version, you're dividing by number of data values. For the sample version, you're dividing by number of data values minus 1. That's really the only difference in the two formulas. Now, why? Remember, the goal of statistics is we want our calculation from the sample to be a good approximation to the calculation for the population. Remember, because we can't get data from everybody in population, so most of the time we're actually just calculating from the sample, and we want our sample answer to be a good approximation to the population. It turns out that if I didn't have this minus 1, the answer for the sample is not a good approximation to the answer for the population. It's too small. So to adjust for that, instead of dividing by n, we divide by n minus 1. And by doing that, it turns out that we do get a good approximation when we do the sample version compared to the population version. So that's why. The variance, the only thing that's different from the standard deviation and the variance, if you look at it carefully, the variance is the same as the standard deviation, except it doesn't have a square root. Right? Same formula, the only thing that's different is we don't have a square root. Which just means that the variance is really the answer we get right before we take that square root. So if we look back on the front page, this was our final answer, but the answer that you get right before we took the square root, which was the 27.5, that's the variance. So this is the variance. For this class, we're just going to focus on the sample standard deviation because in reality, we can't get data from everybody, right? So we're most of the time only working with a sample, which is why we're just gonna, for this class, we'll just work with the sample standard deviation. Now, if you happen to be able to get data from everybody, then you would use this formula. And the only difference, once again, is instead of dividing by n minus 1, the data values minus 1, you just divide by the full data values. Let's talk about how that formula works. We're basically going to do exactly what we did on that very first page, but this time I want to connect it with the formula so we can see where the formula comes from and what it's trying to say. It says here, find the sample standard deviation for the following data set. So sample standard deviation is telling you which formula we're going to use. And like I said, we're going to use this formula for everything. So let me recopy that formula so we don't have to go back and forth. So that formula is standard deviation is big square root. Inside the square root, it's that symbol, x minus x bar squared. On the bottom, n minus 1. Let me make a table just like we did on that very first page. And I want to list my data. So 24, 27, 13, 53, 47, 52. Okay, this is my data. And like I said, in my formula, the x here is my data. Okay, so we're listing out the x's. Now the formula says, so order of operations, we should do our parentheses first. So the formula is saying x minus x bar. What does that mean? X we know is data. X bar we said was the mean. And so what this is saying is take your x's, take your data, subtract the mean. Okay, so I'm going to make a new column that is x minus x bar. So take your data, subtract the mean. We don't know the mean yet, so we actually have to find the mean first. Let's find the mean. Let's do it right here. The mean we know how to do, right? Just add up the data values and then divide by however many data values we have. So add up 24 plus 27 plus 13 plus 53 plus 47 plus 52. And then divide by, we have 1, 2, 3, 4, 5, 6 data values. Divide by 6. All right, so on my calculator, up top, 24 plus 27 plus 13 plus 53 plus 47 plus 52. On the bottom, 6. And I get 36. So this is saying, take your data values, subtract 36. Let me put 36 here. So we're going to take all of our data values and subtract 36. So 24 minus 36. It's negative 12. 27 minus 36. Negative 9. 13 minus 36. Negative 23. 53 minus 36. 17. 47 minus 36. It's 11. And then finally 52 minus 36. 16. So what are these numbers? All right, we took our data, subtract 36. That's really just giving us the distance or the deviations, right? This negative 12 just means that 24 is 12 below 36. This 17 just means that 53 is 17 above the 36. So 17 above our mean. So this column here is exactly what we did on our first page, right? Where we found the deviations. I'm going to say deviations from mean. These are just the distances of our data from the mean. So we did x minus x bar already. The next part is that symbol, which is square it. So what that's telling us to do is to take our deviations and square them. And that's exactly what we did on the first page. Remember, we said that the deviations, we wanted to take the average, but it's a fact that if we added up the deviations, we always get 0. That's a fact of the mean. And the issue was these negative numbers. And the way we got rid of the negative numbers was to square things. So that's where that's coming from. So this is just telling me, take these deviations and square them. So squaring just means multiply by itself. Negative 12 times negative 12. Okay, when we square it, we should always get positive numbers. So this is a positive 144. Negative 9 squared, that's negative 9 times negative 9. That's a positive 81. Negative 23 squared, negative 23 times negative 23. Positive 529. 17 squared, 17 times 17. 289. 11 squared, 11 times 11. 121. 16 squared, that's 16 times 16. It's 256. Okay, so we did the x minus x bar. We did the square thing. What's next? Next is this symbol. That symbol is a summation symbol. That just tells you to add, right? This symbol is saying add up all of these x minus x bar squared. So add up these x minus x bar squared. In other words, add up this column. Okay, the summation symbol is telling me to add up that column. So add up the column. That's 144 plus 81 plus 529 plus 289 plus 121 plus 256. And I get 1420. All right, so we did everything on the top of that fraction, right? We did the x minus x bar. We squared it and got this column. Summation symbol means add that column up, and we did. Next up is divide by n minus 1. So next up, we're going to divide it by n minus 1. Okay, n, what's n? N, remember, was number of data values. Okay, number of data values. How many data values do we have? 1, 2, 3, 4, 5, 6. Okay, divide by 6 minus 1. All right, so let's see what this is. 1420. On top, on the bottom, 6 minus 1. In other words, you're just doing 1420 divided by 5. I get 284. One last step. The only thing we haven't done yet is this square root symbol. Okay, take the square root. Square root of 284. 16.852. Okay, and that's our sample standard deviation. And then just as a trivia here, the number right before we took the square root, this 284, that's called the sample variance. Why do we care about the standard deviation? It turns out that if you know the mean and the standard deviation, you know a lot about your data. Those two numbers will tell you a lot about your data. Let me jump to example 2 and we'll come back to this empirical rule. Example 2. Men's head circumference are normally distributed with mean 56 centimeters and standard deviation 3 centimeters. So I'm talking about head circumference. Head circumference is the distance around your head. So think of it as head size. So I'm thinking about like a hat company would care about how big your head is. So men's head circumferences are normally distributed. Normally distributed just means that when you make a histogram, it looks something like this. Has mean 56 centimeters and standard deviation 3 centimeters. So we know the mean, we know the standard deviation. What can we say about our data? And what we can say it has to do with this empirical rule. So if I know the mean and I know the standard deviation, what I'm going to do is I'm going to fill out this picture. We're going to put the mean in the middle. Okay, what's the mean? The mean was 56 centimeters. So put the mean in the middle. And then we're going to use the standard deviation, which is 3 centimeters, to go up 3 times and then down 3 times. So go up means, add on the standard deviation. 56 plus the standard deviation. So 56 plus 3, that's 59. Plus the standard deviation again, so plus 3 again, 62. Plus the standard deviation one more time, so plus 3 one more time, 65. And then now go the other way. So subtract the standard deviation. 56 minus the standard deviation. So 56 minus 3 is 53. Minus the standard deviation again. So minus 3 again. That's 50. And then finally minus the standard deviation one more time. So minus 3 one more time. That's 47. So put the mean in the middle. And then use your standard deviation and add up 3 times. Subtract down 3 times. And what the empirical rule says is that between one up, one down from the mean is 68% of your data. Between 2 up, 2 down is 95% of your data. Between 3 up, 3 down is 99.7% of your data. So sometimes the empirical rule is called the 68, 95, 99.7 rule. And that just comes from these percentages. Okay, these percentages will always be the same. The numbers right here would be different depending on the mean and the standard deviation of your situation. Now, let me answer these 3 questions right here, part A, B, and C. Part A says, what percentage of men have head circumference between 50 and 62 centimeters? Here's 50, here's 62. What percent is that? 95%. So if I'm a hat company, I know that 95% of people have head sizes between 50 and 62. So if I'm designing a hat, I have to make sure that my hat fits between 50 and 62, and that will take care of 95% of everybody in the world. Approximately 68% of men have head circumference between what 2 values? 68% is between what 2 values? 53 and 59 centimeters. So 68% of men have head sizes that are between 53 centimeters and 59 centimeters. So if I'm a hat company and my medium hat fits 53 to 59 head sizes, that's 68% of the population, right? That's a lot. So more than half of people would wear size medium if that's the case. So that will tell me how many medium hats I need to make. If I'm a clothing store and I'm ordering hats, 68% of the population would wear medium. So I need to order a lot of mediums to account for that. What percentage of men have head circumference between 47 and 65 centimeters? 47, 65, what percent? 99.7%. So almost everybody has head sizes between 47 and 65 centimeters around. So that's 99.7. Now, let me add on some more numbers here. So we have 68, that's 1 up, 1 down. 95%, that's 2 up, 2 down. 99.7 is 3 up, 3 down, okay? Everything is 100%. Okay, that's kind of obvious, right? Everything is 100%. Now, let me add on some more numbers here. What percent would be 56 to 59? If I know 53 to 59, if I know this is 68, 56 to 59 should be half of that, and it is. So 56 to 59 is half of 68, which is 34%. What percent is the middle to the 62? So middle to 2 up, middle to 2 up should be half of the 95. Okay, so middle to 2 up is half of 95. What's half of 95? 95 divided by 2. 47.5%. What about middle to 3 up? So middle to the 65. So middle to 3 up, middle to 65 should be half of the 99.7%. So what's half of 99.7%? 49.85%. And then middle all the way to the right. So middle all the way to the right. Middle all the way to the right is half of the 100%. Okay, so middle all the way to the right, which is just half of that picture, is 50%, because 50% is half. Okay, so basically I just divided these numbers in half, and that will give me middle to the right, middle to 1 up, middle to 2 up, middle to 3 up. Now, it's going to be the same numbers on the other side. I won't write them, but I'll draw the picture. So middle all the way to the right. Okay, exactly the same numbers on the left side. Now, what I also want to add on here is, I know between 56 and 59 is 34%. I want to kind of find out these other numbers also. Like if I go from here to here, from here to here, from here all the way to the right, I want to know what percent those are. And how would we find it? This piece. How would I get this piece? Notice that this piece, I can just go take this piece, 47.5. If I subtract off this piece, that should give me that piece. So this piece here, between 59 and 62, should be 47.5% minus the 34. Okay, subtract those. 47.5 minus 34. 13.5. This piece here is 13.5%. Let me write that. I'll write that down here. 13.5%. What about this piece? This piece is this piece, 49.85%, subtract this piece. If I take this 49.85%, subtract the 47.5%, that should give me exactly this piece, which is right there. So 49.85% minus 47.5% minus 49.85% minus 47.5. 2.35. This piece here is 2.35%. And then I want this piece here, 65 all the way to the right. I can get that piece by doing 50% minus the 49.85%, right? If I take this 50%, subtract off the 49.85%, that will give me this piece, which is exactly the piece I want. So 50 minus 49.85. It's 0.15%. And then we have the same numbers on the other side. So I won't, actually no, I will write. That's 34, so that's 34. Let me write these other small pieces. So that piece, and then the piece all the way to the left. That piece is going to be 13.5. This piece is going to be the 2.35. And then 47 all to the left, it should be the same as that piece, 0.15. Okay, all these percentages will be the same for every single problem. The only thing that really changes is these numbers right here, which you get by doing the mean in the middle, and then use your standard deviation to go up 3 times and down 3 times. The percentages are all the same. Let me actually fill in these percentages just to be complete. This part here is 47.5. This piece is 49.85. And then this piece is 50. And all of those things are percents. I'm going to be lazy here and not put the percentages on there. Now, let's try to answer some questions. We can answer these other questions by just adding the right percentages from our picture on the previous page. Part D says, what percentage of men have head circumference above 59 centimeters? Above 59 means 59 all the way to the right. So I want to add up the percentages from 59 all the way to the right. 59 all the way to the right. This is telling me that I want to add the 13.5, the 2.35, and the 0.15. Right? That's the percentages from 59 all the way to the right. So 13.5 plus 2.35 plus 0.15. And those are all percentages. %. Part E, what percentage of men have head circumference below 62? Below 62, so below meaning to the left, so 62 all the way to the left. So I want 62 all the way to the left. Okay, so I want to add up all of those. But we can kind of be smart here. We know that you can just add up all these, so 13.5 plus 34 plus 34 plus 13.5 plus 2.35 plus 0.15. You can do that, no problem. And that will get you the same answer. But I do know that this entire piece is 50, okay? That entire piece I know is 50, so I can just do 50 plus 34 plus 13.5. And that should give me 62 all the way to the left. So I'm going to do 50 plus 34 plus 13.5. And that's 50 plus 34 plus 13.5. 97.5. Now, once again, you could also just go 62 all to the left, add up all these percentages. 13.5, 34, 34, 13.5, 2.35, 0.15. And you should still get 97.5%. F, what percentage of men have head circumference between 53 and 62? Here's 53, here's 62. I'm just going to add up 34, 34, 13.5. 34, 34, 13.5. %. Part G, what percentage of men have head circumference between 47 and 53? 47, 53. 2.35 plus 13.5. Those two. %15.85%. H, what percentage of men have head circumference between 62 and 66? Here's 62. Okay, I think I did that wrong. That should actually say 65. So what percentage have head circumference between 62 and 65? 62, 65. It's just that piece. So just 2.35%. So as long as you have this picture with the right percentages labeled, all you need to do is look at the picture and that should tell you which percentages you need to add up. And for every problem, these numbers right here will change. Put the mean in the middle, use the standard deviation, go up 3 times, and then go down 3 times using the standard deviation. The percentages should be the same for every single question. All right, that's it for today. Have a great day. See you next time.